Hi everyone, and welcome to another math problem in several variable calculus. Okay, today's problem is express the Laplacian. So Laplacian of f, that in Cartesian coordinates is second derivative of f with respect x plus the second derivative of f with respect y in polar coordinates. So we must write the Laplacian in polar coordinates. So let's see. First, let's recall the polar coordinates. Polar coordinates are when x and y are written in terms of rho and theta. Okay, angle and length from the origin to the point. Now, so we must transform these second derivatives into into the second derivative with respect x and y into second derivative with respect rho and theta, and maybe some first derivatives appear. We'll see why. But let's recall how we change partial derivative with respect to other variables. So, given a function f, the partial derivative of f with respect to x, if we want to change it with respect to rho and theta, is in fact is given by this. Similarly, for the derivative with respect to y. The only thing that it changes is that instead of having x's here, we have y's. Very good. So, using this same formula, we can compute the second partial derivative with respect to x and with respect to y. How? Well, we know that the partial derivative with respect to x changes like this. So, this is nothing else than the first partial derivative with respect to x of the first partial derivative with respect to x. So this is equal to the first partial derivative of this of all these expressions. And now, using that the partial derivative with the partial derivative of the product is the product of the partial derivative of the product is the partial derivative of the first times the second without differentiated plus the first one times the second times the partial derivative of the second. So what we get is almost there. Good. It's all this expression. Very good. Now, for the second partial derivative with respect y and y, we'll use symmetry. So whatever we see in this expression x, we'll replace it by y. So what we will get is all these partial derivatives. Very good. So, what we are looking for is that the Laplacian in terms of polar coordinates, okay, will be this plus this. So the only thing that is left is that we need to compute these partial derivatives. So the partial derivative of rho with respect x, the second partial derivative of rho with respect xx, theta with respect x, theta with respect xx, rho with respect y, rho with respect yy, theta with respect y, and theta with respect yy. Okay? So we must compute all these partial derivatives. So how do we compute these partial derivatives? So we go here. So x is rho cosinus theta, y is rho sinus theta. So from this we get that rho squared is x squared plus y squared. This we know. And theta is the arctangent of y divided by x. Y divided by x is the tangent of theta, so theta is the arctangent of y divided by x. Very good. So these two will be very useful. So let's deal first with rho. So if rho squared is equal to x squared plus y squared, the partial derivative of the left hand side is equal to the partial derivative of the left hand side. So if we perform the partial derivative with respect to x, what we get is 2 times rho, the partial derivative of rho with respect to x, and the partial derivative of x squared plus y squared is 2x. So this tells us that the partial derivative of rho with respect to x is x divided by rho. But x is equal to rho cosine of theta. So in fact this is cosine theta. Good. Now we must compute the second partial derivative of rho with respect to x and x. So we go back again here and then we compute the partial derivative of this with respect to x. And then what we get is rho. No. Sorry. So the partial derivative of rho with respect to x squared plus rho second partial derivative with respect to xx equals to 1. This is cosine of theta, so we get cosine square theta. Okay? So is equal to 1 minus cosine square theta divided by rho. 1 minus cosine square theta is sine square theta. Very good. And now we can use symmetry. Okay? Because notice that if rho squared is equal to this, what do we get when we compute the partial derivative with respect to y? So we will get partial derivative with respect to y. Here we get a y, so y over rho, so we get sine. So we get the partial derivative of rho with respect y is sine of theta. Now when we come back here, partial derivative with respect y, so this will be sine squared, so 1 minus sine squared, so we get cosine squared. So the partial derivative of rho with respect y will be cosine squared theta over rho. Fantastic, isn't it? Very good. Now theta. Again, theta is the arctangent of y over x. So we compute the partial derivative with respect x. The derivative of the arctangent is 1 over 1 plus x squared. So we get 1 plus this times the derivative of what is inside with respect x. And this is what? Minus y over x squared. If we simplify a little, we get minus y, x squared plus y squared. d theta dy, similarly, what we get is 1 plus y over x squared. And now the derivative with respect y is 1 over x. And then multiplying x and divided by x, what we get? X squared plus y squared. Well, second partial derivative of theta with respect x is what? Take this and compute the partial derivative with respect x. Now notice that the only place where x is here. So the derivative is the derivative of the minus the derivative of the denominator divided by the denominator squared. So what we get is 2xy x squared plus y squared. And similarly for y, minus 2xy x squared plus y squared. Very good. If we want to express all these partial derivatives with respect to polar coordinates, here we have minus y is rho times sine of theta. Here we have rho squared, the one we have is minus sine of theta. Rho squared, partial derivative of theta with respect to y. It is 1, so cosine of theta divided by rho squared. This one is, here we have rho to the fourth, rho squared, so we have 2 times cosine theta sine theta rho squared, and this by symmetry is minus this. Perfect, that's perfect. Because we are almost there. So we go back to what we computed, and then we get that the Laplacian is equal to this, is plus this plus let's leave some space here, df d rho, second derivative of rho with respect x, second derivative of rho with respect y. Now with respect theta, theta, what we get is something similar but with x. And finally, we respect just theta, 1 theta. Very good. Now let me fetch the green color, and then we use all the info we got. So, partial derivative of rho with respect to x, what we got is cosine square. Cosine theta square plus sine theta square. So all this is equal to 1. So here we get a 1. Now, what about this one? Here we got with respect to x is sine square of theta divided by rho, and here we got cosine square of theta divided by rho. So what we got is all this is 1 over rho. Very well. Now with respect to theta, so here we got minus sine square of theta rho to the 4. Sorry, that's a plus cosine square of theta rho to the 4. So what we get is 1 over rho to the 4. No, it's 1 over rho squares. And here we saw that this is minus this, so this cancels. So the solution is this plus 1 over rho, this plus 1 over rho squared, this. Okay, so when let me just remark this, where we got it wrong. So d theta dx is this. So when we substitute by rho, we rho sine of theta rho squared, so we get minus sine of theta rho. Okay? And I wrote rho squared, rho squared is just wrong. Super, so thank you very much, and see you in another video.